Guys.
Oi.
For this class, I'm not going to be responding to any private chats. Just a heads up. I don't know if Bob the Builder is here. So, are there any questions on the homework? Does anyone have any questions on any of the problems there?
Can you go over the LeBron James problem?
Okay, I'll go over that one. So let me pull that up here. Where is it? Okay. What if I take out a whiteboard here? Okay. So LeBron James problem here. It's always good to draw out a diagram. So he's shooting from a height of 2 meters. Right? The basketball's coming from here. And the backboard, like this, is 3.5 meters tall. All right, and then it's 10 meters away horizontally. And when it hits the backboard, it's moving perfectly horizontally. All right? When it hits the backboard, it's going to be perfectly horizontally, which means it's Vy. The movement in the y direction is going to be 0. Okay? And it hits the backboard in 0.7 seconds after throwing. Okay, so it's going to get there in 0.7 seconds. So what is the horizontal distance the ball needs to cover in those 0.7 seconds? Well, it's 10, right? Remember this formula dx equals vx times time, right? So basically, using the time, which is 0.7 seconds, we can find out what vx is. So dx is 10. That equals vx times time, which is 0.7. Right, and then if we solve for the horizontal velocity, then it's going to be like 14.29. Okay, and then if you see here that the net vertical displacement here, oops, where is it? I think I lost it. Oh, it's here. Okay, so it's 1.5 meters higher, right? So in 1.5 meters, some vertical velocity here is going to turn into 0. If anyone's new here, I'm going over the LeBron James problem. So after 1.5 meters of going up, the vertical velocity has turned into 0. Okay, so I can use the formula d. I think it's better to use this formula actually. V squared equals V0 squared plus 2AD. Right, and if I have positive here, maybe I'll just have negative here, positive here, then my final velocity is 0. That equals my Vy plus 2 times negative 9.8 times the displacement, 0.5. And so using this, I can solve for Vy. And then with my x and y components here, see how the angle theta, tan theta is Vy over Vx. Okay, so if you were to solve that, that would be how you get the answer. Okay? So I'm going to get started on today's lesson. Let me share my screen with the PowerPoint. All right. Can everyone see the PowerPoint okay? You see it? Okay. So, week 3, dynamics. So what are dynamics? It's another word to describe Newton's laws and forces. So this is basically what most people think about when they hear the word physics. Okay? So this is what, like, the fundamental aspect of physics is, if you will. Okay? So, topics we're going to go over today are Newton's first law, then we're going to go over the second law, third law, and then we're going to talk about weight and normal force, then friction, and finally we're going to talk about force as a vector. So if you did the homework, there's a problem in there where force is described as a vector. All right? So, Newton's first law, I'm sure a lot of you know this one already, and this is the simplest out of the 3 laws. So the law basically says an object will not have any acceleration unless there's a non-zero force acting on it. Therefore, an object at rest must stay at rest unless a net force acts upon it. Okay? And I kind of wrote this one more complicated than how you would teach in school. And so this one basically says that you need force to have acceleration. Okay? So if I have a ball that's stationary with a velocity of 0, if there's no force acting on that ball, then it's not going to go anywhere because its acceleration would be 0. And then since acceleration would be 0, v would never change because acceleration is change in velocity. Okay? So that's basically the first law. So basically, if I had a ball that was going at some speed, I'm just going to say that, and there was no friction, no air resistance, none of that, then this ball would go on forever because there will be no net force acting upon it. Okay? Of course, in the real world, a ball will not go forever because there will always be a force acting on it, as we know, friction and air resistance. Okay, so that is the first law, not that difficult. So here are some questions about the first law. These are more like conceptual questions here. Give you probably 30 seconds to figure these one out. So I think that should be more than enough time. So in a vacuum, so what does vacuum mean? Vacuum means no air molecules. So this is basically no force due to air resistance. Frictionless, no friction, and this is flat. Okay, so this ball is never going to stop, right? Because if we look at the forces upon this ball, we can't find any. There's no friction, there's no air resistance, and it's not sloped, right? So gravity can't pull it down. Remember how gravity pulls straight down? If this surface is flat, then we're only talking about motion on the horizontal plane. And from the last class, we know that horizontal movement is completely independent from vertical movement. So anything gravity does here is not going to change the velocity of the ball. All right? So the answer to this question is no, it will never stop. So if the first law is true, why does a rolling ball on the ground stop? Well, in the real world, we're not going to have a perfect vacuum. We're not going to have frictionless surfaces. So those are the forces acting upon a ball, which would make it stop. Alrighty. Easy to understand. Now the second law. The second law is the most famous equation of all of physics. Okay, it's F equals ma. Okay, if someone asks you to make up an equation about physics, this would be the one that you would turn to. Okay? So a lot of people think that this is actually the hardest law to understand, but it's actually, I think the third law is harder. So I'm going to talk about that later. So this law basically says force is the same thing as mass times acceleration. Let's first talk about units here. So force in physics, we're going to talk about newtons. they're going to be given in newtons, or just N, right? And it's named after Newton himself. And then we're going to have mass in kilograms. So if you don't know what a kilogram is, I think that's about 2 times as much as a pound. And then acceleration from kinematics, we know that must be meters per second squared. So these are the units we have to use when we're calculating force. Okay? So if you've noticed here, we have this little symbol. If you've done algebra, which I'm sure you have, this means sum. Okay? So this basically means that if we add all the forces acting upon an object together, then that equals ma. So what do I mean? Well, in the real world, there's not just one force acting upon an object. Even in a falling object, there's always the force of gravity, right? But there's also the force of air resistance, right? So if we add all the forces acting upon an object together, if we sum all of those together, then we're going to have the object's mass times its net acceleration, okay? And as we know, force is a vector. And this is why vector addition is so important. If we have forces pointing in different directions, like if I had a force pointing in this direction, then we would have to add these vectors together to figure out the net force. All right? And another crucial thing, but mostly intuitive thing to know, is that force is in the same direction as acceleration. Okay? So if I push an object this way, it will accelerate in the same direction. Okay? This is mostly an intuitive thing. Okay, so the problems we're going to work with in Newton's second law are the most basic ones today. So we're going to talk about more difficult ones next week. All right, so that is the second law. Here are some problems for you. Another way we like to write the second law is F net, which basically means net force. Net force is basically the sum of all the forces. Maybe like 5 minutes. So please don't write your answers as a public chat, because we would really want people to work through these themselves before they see the answers. So if you would restrain from doing that, that is highly appreciated. Okay, so as it turns out, I can actually respond to private chats. So if you have an answer, feel free to chat that to me. I will respond. There's a nice smiley face. Draw a head for it. I think we can stop drawing now. Whoa, 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 whoa. So one thing is you shouldn't be drawing unless you finish the problem. Okay, so I'm just going to start going through these now. The first two. So what is the force of gravity on a 10 kilogram object? Oh, remember we have the equation F equals ma, right? If we have an object that's 10 kilograms, that's our m. But what is our a? Well, if you remember, the gravity, the acceleration due to the gravity on the Earth's surface is 9.8 meters a second squared. Okay, so that's a really important number for you to remember here. So if we just multiply 10 times 9.8, we'll get 98 newtons. All right, so that's just a direct plug-in to numbers equation thing. All right, so second problem, a little more difficult. If I apply a force of 100 newtons horizontally on a 10 kilogram object, initially at rest on a flat, frictionless surface, how far will the object go in 5 seconds? Okay, so first thing I see here is that I need to find distance. Okay, and I need to find distance in terms of time. Okay, and what else information do we have? Well, I have a force and a mass. So this basically begs for me to plug these into our equation and find acceleration. Okay, so if I plug in these to F equals ma, I get 100 newtons equals 10 kilograms times my acceleration. My acceleration will be 10 meters per second squared. Okay, so this is going to be my acceleration. So I'm going to be accelerating, I'm just going to accelerate this way. Okay, are there any questions on how I did that? That's a nice arrow. So how far will the object go in 5 seconds? Well, I do have an initial velocity of v0 equals 0, right? Because it's at rest, it's not moving. And I have an acceleration, and I have a time. So the equation I want to use here is d equals v0t plus 1/2 at squared. Okay? Remember these kinematic formulas? So let me define my directions. We have a positive here, negative here. My displacement, please don't draw on the screen. Oh no. Okay, so my displacement, which is what honestly, no. Okay, and my displacement will be equal to my initial velocity times time. Well, that's 0. We can erase this whole term. So my displacement is just 1/2 times acceleration, which is 10. I got from here, times 5 seconds squared. If I solve this equation, my displacement will be 125 meters. All right? Any questions on doing that? Okay, so the last question is actually really really similar to the second one. So a 1,500 kilogram car is barreling towards the edge of the cliff at 100 kilometers an hour, and it is 55 meters away from the edge. What minimum average net force is required for the car to stop in time? So I have a car, it's going at 100 kilometers an hour. and it's 55 meters away from the edge of a cliff. So basically, I want the car to have a v of 0 at the end. And right now I have initial velocity of some value. And if you see here, this is in kilometers per hour. Okay, we're not going to be able to use kilometers per hour in physics. We have to turn this into meters per second. And you could go through all the big processes of calculating that. But I have a little trick here is where if you take a value in 100 kilometers in kilometers an hour and you divide that by 3.6, it will directly turn you it into meters a second. Okay, you can go back and prove that yourself, but this is the trick I'm going to use. If I divide this by 3.6, I'm going to be able to get my answer. So my initial velocity is 27.78 meters a second. Can you guys please just stop drawing on the... Whoever drew these, please erase them. I'm not going to start until you erase those. Okay, no, I'm just going to start now. Okay, so I have a V0. I'm going to have to apply an acceleration to stop this in time. Okay, so this is asking for the kinematic equation v squared equals v0 squared plus 2ad, right? So using the information I have here, I can solve for my acceleration. So I'm going to have a positive here, a negative here. So my v, initial v, well, my final v is going to be 0 because I want it to stop. And my initial v, v0 squared, is just 27.78 squared, which is 771.73 plus 2 times a times my displacement. Okay, and remember that a is going to be negative because I want to apply a negative acceleration for it to slow down. Okay, so it's going to be negative a, and my d is 55. Okay. Now if I solve this, divide by 2, divide by 55, acceleration is 7.02 meters a second. That's the required acceleration. So now I just plug this into my equation, F equals ma, right? I have my acceleration required, and to find the force required, I just need to multiply this by the mass. So my force is equal to 1500 times 7.02. If I do that, I should get 105.00 newtons. All right, are there any questions for how to do that? Okay, who just did that? Okay, please just stop drawing on the screen, okay? I don't like it. I don't think anyone else likes it either. It's just, no, please don't. Okay, so now we have the third law. So a lot of people think that the third law is a rather easy law, but from personal experience, this law is actually the hardest law to understand out of all of the three. Okay, so the law basically says that every action force has an equal and opposite reaction force. Okay, so what does this mean? Well, a common misconception that people have is that, for example, if I push on a box here with a force F, well, this action force, me pushing on the box, is going to have some equal and opposite reaction force. So what does that mean? Well, a lot of people think that, well, there's going to be a reaction force pushing it at the same magnitude, right? Well, if we have these two forces pushing together, isn't this like, don't these forces balance out? Does that mean that I have no net force? So how can anything move, right? Because based on this logic, it seems like the third law, like, it doesn't make sense. So this is a common misconception people have, and this is one that I had for a very long time. And it's really important that you guys recognize this early on. So the way most people write the law is actually really misleading. So we have two forces involved here. And the key thing to know is that these forces are not being applied on the same object. Okay, for example, if I have some object A applying a force on B, just like me as A and then the box as B, right? I'm applying a force on B. The equal and opposite reaction force is a force that B pushes on A, okay? So the reaction force is actually being applied to me, the human, okay? So it's not being applied to the box. Okay, so the reaction force here is not on the box, but rather on the human. The box is pushing the human at a force backwards. Okay, so this actually makes sense, right? Because when you're just walking by yourself, that's actually pretty easy. But if you're pushing a box in front of you, it's going to be harder to walk forward. So that's because you have to overcome this force of the box pushing you backwards. Okay, so this is the third law. And it's really important that you know how this works. So are there any questions on how the third law is working? How? So does anyone have any confusion?
Is it the same thing to gravity?
Okay, so I have an example with gravity in the next slide. So I'll have you work through that, and I'll talk about that later. These are more of conceptual questions here. Maybe I'll give you 1 minute to do these. Think about them on your own. Okay, so I'm just going to talk through these. How do rockets move? Well, if we draw a rocket here, this rocket is going to have some gas particles that it's going to force out behind, right? So it's going to apply a force to gas particles. That's why gas shoots out of the back of the rocket. So in this case, rocket applies a force to the gas. So the equal and opposite reaction force is the gas applying a force to the rocket in the opposite direction, this way. Okay, so that's how a rocket is propelled forward. The gas is actually pushing the rocket forward. And the same thing goes for cars. If we have a wheel here, the car pushes the ground backwards, right? Pushes the ground backwards, and the ground will push the car wheel forward. The same thing with the human foot. The human foot will push the ground backwards, and the ground will push the human forward. Okay, are there any questions? Okay, so the last one is actually a really common question. Okay, Autumn has a question.
Yeah. So for the box, if it gives an equal reaction force, then it's going to be impossible to move the box because then it's going to push you back equally if you try to push it.
Okay, so that is a common misconception that a lot of people have. That's a really, really good question. And personally, I had this question for a long time and nothing would explain it to me. So the third law says that every action has an equal and opposite reaction force. Okay? It's a terrible drawing. But if I apply a force onto the box, the equal and opposite reaction force is not a force applying to the box. Nothing is forcing the box backwards. The box is forcing me backwards. Okay? So how do I still move forward? Well, there's the muscles in my leg that are pushing me forward. And when I push forward, like in this example, I'm doing the third law with the ground here. Okay? So I can use my muscles to push myself forward. So I still need to overcome this force that's pushing me backwards by the box. Okay? So this is how the third law works. The box is going forward, but I'm also going forward because of the muscles in my leg. So I can draw out another force here if you wanted to, of the force in my leg. Okay, does that clear things up?
Yeah, thanks.
Okay, so the last one is actually a really common problem. So the earth exerts a gravitational force on an apple in a tree, causing it to fall. So what is the equal and opposite reaction force in this situation? Well, if I draw an apple and an earth, not to scale. The earth is going to pull on the apple this way. This is the force of earth on the apple. Well, according to Newton's third law, the apple will pull on the earth. So the cool thing here is that the apple is actually pulling a gravitational force on the earth. Okay, if I have an eraser here, my eraser is actually pulling a gravitational force on the earth. And if I drop this, just as the earth pulls the eraser down, the eraser is actually pulling the earth up. Okay, so if we have a force here, the eraser is pulling with an equal force on the earth. So why doesn't the earth accelerate up just like the eraser would? Well, since the earth has such a big mass, F equals ma, the acceleration of the earth is going to be a lot smaller than the eraser here. Okay? So the earth will accelerate up by a really, really small amount. Okay? So even with really small objects, they're exerting gravitational forces on each other. So the apple, the answer to this question is that the apple is pulling the earth up with its gravitational force. All right? I know it's kind of unintuitive. Okay, so now we have weight and normal force. So normally when we talk about weight in our daily lives, I could say like 100 pounds, right? And there's the unit of weight that we use in daily life with the kilogram, right? 100 pounds is around 40 kilograms or so. But in physics, kilogram can only be referred to as mass, okay? Kilograms are not a unit of weight in in physics, okay? So weight, by definition, is the gravitational force on an object, okay? So what is that? That's F equals ma. And the acceleration due to gravity is mg. So this is the definition of weight. Mg is weight, okay? So that's why if I were on a moon, I would weigh less, but my mass would be the same, okay? So since weight is a force, we're going to be using newtons as a unit of weight in physics, okay? So normal force is the force a surface exerts on an object resting on it. If I have an eraser resting on the table here, there's the force of gravity pulling it down, but it's not falling. Why? Well, there's a normal force that the table provides up, which will support the eraser on the table. Okay, and normal force always opposes weight. Okay, and another thing to know is that normal force is perpendicular to the surface. So if I have a table here with a box on it, there's going to be a gravitational force mg pulling it down and a normal force pushing it back up. Okay, and if this thing were inclined like this, then normal force would be slanted a little bit. And we're going to talk about inclines next week, but this is basically the definition of normal force. So the normal force is the force that a surface exerts on an object upwards to support it. Okay? So there is always a normal force. As you guys are sitting in your chairs right now, the chair is exerting a normal force upward on you. Okay? So why do we use normal force? We're going to use that in friction, and we're going to talk about that later. But first, let's do some exercises with normal force. Okay? And I'll give you 2 minutes to do this. So if you get an answer, please private that to me. just to clarify, in the third part of the second problem, the person is no longer standing on the box, okay? So it's just a box and me pulling up. Okay, so sorry for any confusion. So in the third part of the second problem, the person is no longer standing on the box. It's just the box and me pulling up. I'm just going to go over the problems now. So the first one is relatively simple. Okay, so it's always good to draw out a diagram. I'm so terrible at drawing, I'm just going to draw a box as a lamp. Okay, so let's look at the forces acting on this box. There's always the force of gravity pulling it down. Okay, but there's also normal force that the table will exert up on. I'm going to label that as n. Okay, so be careful not to confuse this n, this variable, to unit newtons. Okay, so this is not in units, this is just a variable n. Okay, so since the lamp is resting on the table, it's not moving anywhere. That means it has no net force acting on it. Remember this? The sum of all the forces acting on it is 0, because otherwise it would have some kind of acceleration and it would be moving. Okay, so if we sum up all the forces on this object here, this lamp, we're going to have a value of 0. So I'm going to set 0. Now I'm going to find all the forces on this object. So I'm going to find a positive here and a negative here. So I'm going to have a positive mg force, okay? Because that's pulling it down. And the direct vector opposing this is my normal force, and that will be negative, okay? And these things added together will equal a net force of 0, okay? Are there any questions about this? So now with this equation, all we need to do is just solve it, right? Because we do have m, which is 4, and gravity. So n is just mg. The normal force is going to be 4 times 9.8. Plug that in the calculator, 39.2 newtons. Okay. The second one has a little more steps into it. So I have a 10 kilogram box resting on the floor. What is the normal force acting on the box? So this box is just sitting here. Again, I have an mg pulling it down. I have a normal force pulling it up. Okay. So my net force is still 0 because it's not going anywhere. And if I define a positive and a negative, then my 0 will equal to mg minus n, just like the first problem, and n will equal to mg. And therefore, I will have 10 times 9.8, 98 newtons. So that's the answer to the first part. Let me just clear all. So what is the normal force if a 50 kilogram person stands on the box? So just to draw this out, I'm just going to draw another box to represent a person. Okay, so we have, let's draw out all the forces here. Well, we have the forces of gravity. One is acting on the box, which is mb. I'm just going to label that as the mass of the box times g. And then we have another force pulling down, which is the mass of the human times g. Okay, and then the only force pulling up is the normal force supplied by the table. Okay, are there any questions about that? So basically, this is still at rest, so I have no net force. So my net force is still going to be 0. So now if I just establish a positive and a negative here, I'll see that since mbg is pointing down, that will be positive. mhg is also positive. And then I have a normal force pulling up, which is going to be negative. Okay, so now I just need to solve this for n. N will equal to mb plus mh times g. So now I have mass of the box plus the mass of the human times 9.8. Normal force equals 588 newtons. All right. Now the third part. What if I pull upwards on the box with a force of 10 newtons? I think that's 10 newtons. Yes, it is. Okay. So again, I'm going to draw out a diagram. So there's going to be an mg force pulling down on the box, but I'm going to be pulling up with 10 newtons. And there's still going to be a normal force, always. Okay? I've drawn out all these forces. I can use 0 as my net force because it's still not going anywhere. 0 equals, well, positive here, negative here. My mg will be positive, and that's going to be minusing a 10 minus my normal force. So now I just need to solve. Normal force is mg minus 10. So now that the human is not on the box, all I have is a 10 kilogram. 10 times 9.8 minus 10. Normal force is 88 newtons. All right, so this shows how important it is for you guys to draw out these diagrams. Okay, if you were to just look at the problem and be like, I don't really know where everything is, it's really important to draw out a diagram, and it really clearly shows all the forces you need to consider. Okay, so the key thing here is that if I missed any of these forces in my calculations, then my answer would be wrong. So this is why it's really important to think about all the forces acting on this box. Okay, are there any questions? Good. Okay, friction. So first, let's ignore this table here. Let's just ignore that. So friction, the definition of friction, we know that friction is applied on every single object in the known universe. Okay? And friction, if I had some object here on the table and it was moving, then we will have a friction applied to it. And the definition of friction, the force of friction, is the normal force. This is why we have normal force as a topic. Normal force times a coefficient of friction. And this thing is called mu, like the noise cows make. And I don't know why it's called that, but that's the way it is. Okay, so this is the coefficient of friction. Okay, and we can find these coefficients of friction in this table here. Okay, so every single interaction between different surfaces has a different mu, has a different coefficient of friction. As you can see, if we have rubber against concrete, this number is going to be larger, and it's going to contribute to more friction than if I had them on ice. All right? So the larger the mu, the coefficient of friction, the larger our frictional force. And that's given in this equation here. And a lot of people think that instead of writing the normal force, they could write mg, the weight. But actually, it's really dangerous to write that because there's also a lot of lifting and pushing down that could be applied to this object. So we have to use normal force times the mu. Okay? And so, a lot of people also think that friction is dependent on surface area in contact with the ground. Right? If I had some piece of paper on the ground, intuitively, if I were to crumple this paper up into a ball, there would be less friction. But according to this formula, this is not true. Friction is not dependent on surface area. Okay, so the force of friction on this flat piece of paper on the table is the exact same force of friction on this crumpled up ball. Okay, it only depends on the normal force and the coefficient of friction. All right, so this is a common misconception that this frictional formula basically busts this myth. Okay, so frictional force only depends on the normal force. Okay, and as you can see here, we have two different types of friction. We have a static friction and a kinetic friction. So let's first talk about kinetic friction, Fk. Kinetic friction has the same formula, N, but multiplied by a kinetic coefficient of friction. Okay, as you can see here, most of the time, the kinetic and static coefficients of friction are different. Okay, so this is the equation for kinetic friction. So, and kinetic basically means moving, right? We have kinetic energy, which we're going to talk about later. And kinetic basically means moving. And this is the friction that applies to all moving objects. Okay? So if I have something going forward with velocity v, then I'm going to have backwards kinetic friction applied on it. Okay? So kinetic friction intuitively always opposes motion, okay? It only depends on the direction of the velocity of the object. It's always in the exact opposite direction, okay? So even if I had a car that had its brakes locked and the brakes were pushing it backwards, a braking force, but it was still going forward, its frictional force would still be backwards, okay? Frictional force, the kinetic friction force does not depend on the forces acting on this object. It only depends on the direction of the object's velocity. All right, so this one is actually one of the easier one to understand. So then we have static friction. This is the same formula, but times a new coefficient of friction, okay? But actually in this formula, we have a greater than, less than, or equal to. So what do I mean? Well, static friction is the friction applied to any object at rest. Okay, if I had a big box here, okay, we all know that if I apply with a teeny tiny force on this box, it's not going to move, right? It's not going to move because there's going to be a static frictional force opposing my force trying to push it forward. Okay, so static friction is the frictional force trying to stop an object from beginning to move. Okay. So in this case, if I were to apply a really small force on the box, the static friction would be really small, trying to oppose my really small force, okay? If static friction was greater than or less than my pushing force, then my net force wouldn't be 0, right? Then this box would start moving. But since it's not, my static friction has to match my force applied. If I apply just a little more force, but the box still doesn't move, the static friction grows as well to compensate. Okay, so static friction is not a static value. Okay, if this makes sense. Static friction is actually a changing value. It depends on the amount of force that I'm applying to the object. If I apply more force, then static friction will increase. All right? Does anyone have any questions about this? Okay, so why do we have a less than or equal to? Well, if we plug the static friction coefficient into this equation, this is going to give us the maximum value that this static friction can hold. Okay, so as we know, if I were to apply a bigger force on this box, it will start moving, right? So that's when it overcomes the static friction force. Okay, so there's a certain point where static friction cannot it reaches a maximum point. Okay, and once a pushing force exceeds this maximum point, the box will start moving, right? So if we plug this into our equation, our maximum force is given by the coefficient of friction, okay? But our static friction, our actual force, can be smaller, right? As I said, with these small forces, the static friction can be small as well, okay? So static friction is basically gonna vary from a value of 0 to its maximum, which is the normal force times us, okay? Are there any questions? Is there anything that I could clarify here?
I have a question.
Okay. Yeah, what's the question?
So if the force is velocity is 1 point, if the force is 1.1, then what would the net force be?
But could you ask that again?
If the force of rubber on dry concrete is 1.1, then what would the acceleration be?
Okay, so this is just a coefficient of friction. Okay, as you can see here, that this number, if we plug this into our equation, it's going to help us get a value for our coefficient of for our frictional force, right? But this value also depends on our normal force. If we have heavier objects, then it's going to have a greater normal force, right? Because the ground is going to have to exert a greater force to keep that object up, right? So if we have a bigger object, a heavier object, that's also going to contribute to a greater friction, okay? So these numbers here are not values for our force, okay? Not force. The force is given by this equation here, okay? And also, guys, don't try to memorize these. And these are going to be given on the test if you're ever going to take one, okay? So there's no point in memorizing them. So now let's do some problems with friction. Let me first stop this. Let me write the equations here. Maybe one more minute. Okay, I'm just going to explain the first one now. So if the normal force on an object is 60 newtons, the coefficient of static friction is 0.3, what is the minimum force required to move the object? Well, Let me just draw this here. We have a normal force here. Right? And now we can just plug this into our equation for static friction. Force of static friction is going to be less than or equal to my normal force 60 times my mu s 0.3. And that's going to be 18. So what does this mean? Well, my static friction force is going to be anything equal to or less than 18. Okay, so it's never going to be able to go over 18. So once my pushing force here exceeds 18 newtons, it's going to start moving. Okay, so all I need to do is exceed 18 newtons or just be barely above 18 newtons. So I can just write 18 newtons. Okay, for simplicity's sake, that is the minimum force required for the box to move. All right, is there any questions here? Okay, the second one, an 18 kilogram box is sliding on a rough surface with a coefficient of kinetic friction 0.5. If it is moving at 10 meters a second, how long will it take for the box to stop? Well, using our equation here, we can calculate the force of kinetic friction on this object. Okay, so let's first look at the normal forces acting on this. We have an mg pulling it down and a normal force pulling it up. Okay, and if we look in the problem here, just to make sure, there are no other vertical forces acting on the y-axis. If you look at the forces in the y-axis, it's not moving up and down anywhere, so it's 0. 0 equals mg minus n if I were to do this. All right, so my normal force is just mg in this case. All right, so what is my force? Well, my force would be n times 0.5, correct? This would be my kinetic friction. And let's just pretend the box is moving this way, right? So if we plug these values into our equation, our Fk is going to be mg times 0.5. All right? So using this, we can solve for the acceleration of our object, since F equals ma. Since our friction force is the only force being applied on this object, we can just directly plug this into F equals ma. So this, all this, let me move this aside, equals ma. All right, and since we have m units on both sides, we can cancel those. So our a is just 0.5 times gravity. Okay, so that's my acceleration of the box. So that's the acceleration that's stopping the box. All right, so if we calculate that, that is 4.9 meters a second squared. So my initial speed is 10 meters a second, right? So if we use the definition of acceleration, that's just the change in velocity over time. V minus V0 over t, back all the way 2 weeks ago to the first lesson. And since we have a V0, and this is just a difference in velocities, right? We're starting at 10, we're ending at 0, our difference will be 10. All right, so this will be 10. And our acceleration, 4.9. If we solve for t, t equals 10 over 4.9. Do that on the calculator, 2.04. All right, so this is a problem that uses both kinematics with normal force and also friction as well. Okay, are there any questions about this one? So I think that is all the time I have left for today. Would you guys want to stay a little longer? We're going to go over our last topic. Would that be okay with you guys? If not, then I can just end the lesson right now. Are there any objections? I can go on if you want. Okay, I'm just going to go on. So let me skip this one just for now. Okay, so now we have force as a vector. Okay, if you did the homework, there's a problem on that about force as a vector and force as a vector. So that's pretty redundant, but since force is a vector, and we have the equation sum of all f's equals ma, we can add all the vectors of force on an object. For example, all of the questions we did were in one-dimensional force. They were either going this way or that way, and we could just add the magnitudes, right? So that's how we can do vector addition in the same direction. But what if forces were in different directions, right? So at this point, we're going to have to use the skills of vector addition to solve for the net F, all right? So just to review a vector addition, we have to divide each vector into its x and y components and add those together, and then find our final vector, all right? That is how we find sums of all forces as vectors, okay? Let's work through this problem here. Who's drawing again? Please stop, please stop. Please stop drawing those arrows. You have a pretty good idea of who is drawing those, so please stop drawing. I know who you are. All right. So that is basically the last strike I'm going to give you. If there's any more drawing on the screen, I'm going to contact your parents. Yeah, I should disable annotations from other people next time. So I'm just going to go through this problem here. So what's really important is to always draw a force diagram. Okay, so I have a 5 kilogram box sitting on a frictionless floor, which means I can just ignore all friction that might occur, and I pull it straight up with a force of 100 newtons. My friend pulls it straight to the right with a force also 100 newtons. And remember, we have a gravitational force pulling this box down, mg, okay? You cannot forget this gravitational force, okay? So if we analyze our forces in the y direction, well, these are both going straight up, we can just add them. That force in the fy direction is just, well, if I define positive as up, negative as down, it's just 100 minus mg, and mg is 5 times 9.8, so 100 minus 49, 51. Okay, so if I take this point value as my box, there's a 51 Newton force pulling it up. And to the right, I'm gonna have 100 newtons. There's no friction going on there. So that's the only force to the right. Okay, so now I have my two components. I can just use the Pythagorean theorem to make this into a triangle, right? So I'll just do 51 squared plus 100 squared, take the square root of that. Let me just do that real quickly. 12.25 Newton. All right. So how do I find the direction? Well, if we have a theta here, then the tangent of theta is 51 over 100. Take the negative tan. That's just tan negative 1 of 51 over 100. 27. Right, so this box is basically gonna fly. It's kind of gonna fly up like that. Okay, which is kind of unrealistic here to say, but that's the way it is. Okay, so let me see if there's another problem here. Okay, let's do this one instead. So this one is pretty important here. This is basically a problem that will comprise all of the topics we learned today. So class will be over when we go through these two problems. And I know that I've passed time, so if you guys really need to leave, you can feel free to do that. Okay, I'll give you 1 more minute to do these. Okay, I'm just going to go over the problems now. So I have a 50 kilogram box. I'm going to pull it at 40 degrees to the horizontal. Okay, some force. Okay, so what is the minimum force needed for the box to lift off the ground? Well, that's essentially the lifting force that's going straight up, right? Because when I apply a force like this, it's going to have an X component and a Y component. And the Y component is what we're going to use to lift up the box. Okay, so on the box, we have mg, right? So our Fy, our Y component of force, will need to overcome our mg. Okay, so that's going to equal to our mg. So Fy will have to equal to 50 times 9.8. Let me do that real quick. 490. So our Y component of force will need to be 490. So what is our actual force? Well, if we use the angle here, we can see how the Fy is the actual force times the sine of 40. Okay, and if we plug this one in, 490 equals F sine 40. F equals 490 over sine 40. Doing that, we're going to get 762.3 newtons. All right. And now for the last problem of the day, if I took the same box and I pulled at a 50-degree angle to the horizontal at 100 newtons, what would its acceleration be if the coefficient of friction was 0.4? Okay, so I have a 50 kilogram box and I have mg pulling it down. Okay, and I'm applying a 50-degree angle, 100 Newton force. Okay, so again, I'm going to have an Fy and an Fx. Okay, so let's first look at the y direction. So obviously, if I'm gonna calculate the friction force that's trying to resist this box from starting to move. Okay. So basically, how to calculate the friction force? Well, all I need to do is find the normal force acting on this box. Well, if I apply my normal force in this diagram, then I have here. So basically, my normal force plus my y force is equal to my mg. Right, so normal force is equal to mg minus my Fy. Okay, so what is my Fy? Well, that's just the sine of 50 times 100. 76.6. And if I subtract that from 50 times 9.8 minus that, then my normal force, 413.4. And so, if I take my coefficient of friction, then the static friction force on this box has a maximum of n times 0.4, which is equal to 165.358 newtons. All right, so that's the maximum static friction force. So now I'm going to take the forces in the x direction. Right, let me clear up a little space here. So basically, my x component of force is trying to overcome the static frictional force. Well, if I calculate that here, that's just cosine 50 times 100. Oops. That is 64.27. Well, obviously that's not enough to overcome my static friction force. All right. So therefore, this box is not going to go anywhere, right? It's not going to have any acceleration. So the answer is actually 0. Okay, are there any questions? No? Okay, that's good. Okay, so let me stop sharing. And I'm going to summarize all the key points here, right here. So the key points, second law, sum of all forces equals mass times acceleration, okay? And then we have weight is equal to mg, and then normal force is the force surface exerts on an object. Okay, if I have an eraser on that table, the table's going to exert a normal force on the eraser. Right, and then what other key points do we have? We have friction here. We have kinetic equals the normal force times mu, okay? And then we have the static. All right, so those are basically the key points that you should know from this class. And so if you want to take a screenshot of this, feel free to do that now. Alrighty, so let me stop sharing. So that's the end of class. Thank you guys for staying this long. I'm sure it's really late now in the night. So hope you guys have a good weekend. Goodbye.
Thank you. Bye.
Bye.
Thank you.
Thank you.
Bye.
Bye.